So my dear engineers, here we're going to be looking at mechanical power transmission by shaft. So in this area, we will derive the formula for the power transmitted by shaft and combine it with torsion theory. And we know that the torsion equation says that G theta divided by L is equal to T out of J is equal to tau out of R, whereby this is the radius of the shaft, this is the shear stress, this is the torque transmitted, this is the polar second moment of inertia, G is the modulus of rigidity, then theta is the angle of twist, which can be given in either radians or degrees, and then L is the length of the shaft. So let's look at, first of all, mechanical power is defined as work done per second. So mechanical is equal to the work done per second. So now, work done is defined as force times the distance moved by the force. So work done is equal to the force times the distance moved by the force. So that means if we want to get power, this will be F times X, whereby X is the distance. Then if we want actually, this is going to be power, and then it will be in per unit time, work done per second, whereby we get force times distance, that is the work done, then per unit time, which is T. And so what does that mean? P is power, X is the distance moved, T, that is the time taken, and then F is the force. Now, if you analyze that equation very well, this is the force times X out of T. But X out of T can be the same as velocity if X is displacement. So we shall be talking about the vector quantity displacement. So if we divide it by time, we know velocity is the rate of displacement of an object with respect to time. So that means our power will equal to force times velocity. So that is another equation. So this is 2, this is 1. So you can see how we can calculate power given the force and the velocity on the body where the force is applied. So now if we look at the force rotating at radius r, traveling one circumference in time of one revolution, the distance moved in one revolution is going to be x equivalent to pi r. We are talking about distance of one revolution. So what does that give us? It will obviously tell us that if we have one revolution, then we can talk about a number of revolutions per unit time. So if the speed n, if we talk about n revolutions per second, okay, then the time of one revolution is going to be what? So if we are saying that n revolutions, we are talking about 1 second as time. What about if we have one revolution? So the time will be 1 out of n seconds. So for one revolution, power transmitted would be, remember we have power, which is equivalent to F times X out of T. This is going to be, we have already seen that for one revolution, we need 1 out of n seconds, that is time. So that means our T will be 1 out of n, and X will be 2 pi r, because it is one revolution. That means we are moving around a circle of radius r. So that power will therefore be F times 2 pi r times, this is actually going to be divided by T, which is 1 out of n. And this becomes 2 pi n times r. So our power for one revolution will be 2 pi n r times F. This is multiplied by F. But Fr is the same as torque. This is what we are meaning. We are applying a force here, and then the perpendicular distance is R, and this is F. And we say the torque is a moment of a force. So that means power will therefore equal to 2 pi N times what? Times torque. So this equation itself is very important. So we can further modify this. So modification of this equation, we shall take 2 pi N to equivalent to equal to omega. So omega is actually what we call the angular speed. So meaning power will be 2 pi nt, and this is the same as omega t. But here we consider the n to be revolutions per second. If we found that if n is in revolutions per minute, like it is always the case, then that n, the new n, okay, this n becomes, that new n will be this n divided by 60. So meaning you can always have power equivalent to 2 pi N out of 60 times T. And this is always the case if you have the speed of the shaft or speed of rotation as revolutions per minute. So to convert it to revolutions per second, we divide it by 60. So we must also note this. So let's look at an example here. So we are told that a shaft is made from a tube. The ratio of the inside diameter to the outside diameter is 0.6. The material must not experience a shear stress greater than 500 kilopascals. The shaft must transmit a power of 1.5 megawatts, that is mechanical power, at a revolution per minute of 1500 RPM. Calculate the shaft diameter. So here we have been given the speed in RPM, which is revolutions per minute, and then we are given that the maximum shear stress is 500 kilopascals, that is tau max. So here we're going to use the torsion theory and the power equation. So first of all, if we are to determine the diameters, we shall have to use this formula. We know G theta out of L is equal to T out of J is equal to tau out of R. Okay? Then we know that power is equal to 2 pi N out of 60 times T. And then we know that J is equal to pi out of 32 into D to power 4 minus small d to power 4. But here we can just proceed and see that we are given that the ratio of inside diameter, that is D, small d divided by capital D, is equal to 0.6. So meaning we can actually express D, this small d, in terms of capital D. So we can have this small d equivalent to 0.6 of capital D. So now we can determine our J, polar, this is polar second moment of inertia. So this will be pi out of 32 into d to power 4 minus 0.6 d to power 4. So what is the polar second moment of inertia? This is pi out of 32 into capital D to power 4 minus. If I power this, I will have, so this is going to be 0.1296 d to power 4. So this is going to be pi out of 32. Then I put out d to power 4. So into, this is going to be 1 minus 0.1296, and this is going to be pi out of 32 d to power 4 times 0.8704. So if now I remove that constant pi out of 32, So J becomes 0.08545. 0.08545 d to power 4. So we keep that. We can get T, which is equivalent to power divided by 2 pi n out of 60. And this is going to be, we already know that power is 1.5 megawatts. So 1.5 times 10 to the power 6 is given in the question here. 1.5 megawatt. So that is 1.5 times 10 to the power 6. Then this 60 shall go up. Then we divide it by 2 pi times n. N is now given as 1500. So the proper calculation of T on our calculator will give us 9549.3. So this is in a Newton meter. We are looking for the diameters. So we can apply T out of J equivalent to tau out of R. And then we substitute in, we look for this R, we can express it in terms of capital D. We know this R is always equal to capital D out of 2. So we can now apply in torque, we know it as 9549.3 divided by 0.08545 d to the power 4 equivalent to tau. Tau is known is 500 kilopascals. That is 10 to the power 3 pascals. Then divided by tau is the maximum shear stress that we have here. So 500 kilopascals. Then we are dividing it by R, which is actually D out of 2. So that means this and this will go, but we create a tube here. So if I cross multiply again, I will have D power 3, which now will be, if we cross multiply, this D will come here, and then, so we'll have 9549.3 divided by 500, but times 2. This 2 will move up, okay? To move up, so this and that will go. So I will have times 10 to the power 3 times 2 here, then times this value here, 0.08545. So obviously we shall be looking for the cube root of this. So this will be 9549.3 divided by 2 times 500 times 0.08545. Then our D becomes 0.4816 meters. And this is 481.6 millimeters. But D, small d is 0.6 of capital D. So this becomes 0.6 times 481.6. And then this becomes 289 millimeters. So the diameters have been calculated as required by this problem.